Welcome back, students, to another class of design of steel structure. In this video, we are going to learn about how to do design of gantry girder. Now, you must be wondering what is a gantry girder, right? So, quickly, just let us learn what a gantry girder actually looks like and uh, what are the functions that what are its functions in day-to-day life, right? So gantry girder is basically you can see in any industrial area, maybe any infrastructural projects where you have to build skyscraper or maybe railway bridges, so and also industrial sheds. So gantry girder you have you have all of you have seen in case of industrial shed there is a structure uh, which is resting on a railroad located at a certain height, and it is moving and taking up something from one point and dropping it at some other point, right? So I'll just show you a simple diagram and explain what a gantry girder actually looks like. So this is a simple diagram, schematic diagram of a gantry girder. So a gantry girder is nothing but a kind of beam, or you can say it as if the span is much larger, you can also refer to as it as a plate girder. But how is it different than in any beam or plate girder, so that we have to name it in a different manner? So gantry girder basically is not a one single thing, it's a combination of a system. Combination, by what we mean by combination of a system, so if you see this diagram here, all right, this structure that you see here, which looks like a beam, okay, so this is your gantry girder. And what is the purpose of this structure? It basically supports another structure which is resting on it through wheels. You see two wheels are here, and there is a railroad that is provided. So these two wheels will be moving through this railroad which is resting on top of the gantry girder, right? So if you look closely, there is two wheels on this side and there is another two wheels on this side as well, and there is another crab. This arrangement here is called crab. This is also able to move in like this, in this direction. So whatever, at whatever position you have to pick something, so it can adjust itself by moving longitudinally or transversely, and then this is called cross travel and this is called hook. So this picks up the stuff and then drops it at whatever required position you need to drop it. So this whole arrangement is a truss girder arrangement, and the uh, structure, that is the member that is supporting this whole mechanism, is the gantry girder. Okay, so what are the different functions that it does as compared to beams or plate girders? Nothing much actually, but in addition to bending moment, shear force, it undergoes certain lateral impact load, axial impact load, due to the movement of this mechanism here, right? So just I'll, to give you an idea, I'll just discuss this a small thing here. This crab you see, like I mentioned, it can move in this direction as well. Okay, so just imagine it is moving like this and suddenly comes to a halt, or vice versa, it is at a halt and suddenly starts moving. So automatically this crab will put a lateral load on this railroad, and consecutively this railroad will transfer that lateral load to gantry girder as well, right? So this is one case of scenario where lateral load can come onto the gantry girder. Secondly, just imagine the whole mechanism here starts moving in this direction, that is the longitudinal direction of the gantry girder. Okay, uh, say it is at a halt and then suddenly starts moving, or vice versa, it is moving and suddenly comes to a halt. Due to the inertia, it will again uh, initiate, or it will create a axial thrust within the gantry girder itself. So these are the types of load that are usually not seen in case of your beam structure or plate girder. All right. So to consider those loads, to consider those design consideration, there will be certain uh, small changes while designing any gantry girder. However, the overall procedure mostly remains same. First, you determine the loading conditions, and then find out the shear force bending moment, maximum shear force bending moment that will be coming, and accordingly choose a section and then find out its capacity, shear force capacity, bending moment capacity, shear force capacity, and all other stuff that you did in the last class. All right. So, the only thing that is majorly different in this case is basically the loading conditions. Since as you can see, there is a whole mechanism and different loads will be coming on it. So we have to make sure that we accurately calculate the loads, and since the loading pattern is different, unlike the plate girder or beam problem, if there will be given a, UDL and you simply calculate W square by it. Unlike those cases, here the loading condition is different. You see, this hook will be taking certain load, which is basically called crane capacity. That is how much the crane can pull up, or how much capacity does the crane has to take the weight. So this whole mechanism will be taking certain load or certain weight, and also in addition to that they have their own self weight. So this whole mechanism, which is taking certain load or having some weight, will be eventually passing the load onto the gantry girder, not by the mechanism of uniformity, right? Since it is connected with two wheels on the gantry girder, so we can easily say that the whatever weight that this crab portion is having will be transferred to the gantry girder through these two wheels only, two wheels on this side, two wheels on this side. So when calculating loading conditions, while finding out bending moment and shear force in gantry girder, you must know what are the weights that are coming to the crab, and you must know how to convert that load into the load on the gantry girder. So that is the major difference as compared to beam and plate girder. Here you have to find bending moment, shear force through different calculations, and it is quite different than the earlier cases. All right. So this is a basic typical arrangement of gantry girder. You can see usually what happens, there is a column, there is a stepped column, and the gantry girder is resting on the half part of a column, and the other half is taken up. Above the gantry girder there is a crane wheel on which a railroad on which a crane wheel is situated, which actually helps move the crane girder in the longitudinal direction. And then there is a, on the crane girder there is a crab which moves in the transverse direction as well. So I hope this diagram is very much clear to you. Moving on. So these are the different mechanism how a gantry girder can be connected to the railroad. The I section in the bottom is basically the gantry girder, and the I section on the top is the, it signifies the railroad. So these are the So these are the main loads that will come onto the gantry girder. There is a vertical load which is due to the obviously due to the load weight by the crane girder, transmitted by the crane girder, and then there is a lateral horizontal load which comes to the structure when there is a movement of the crab in the transverse direction, and finally when the crane girder moves in the longitudinal direction, there is a horizontal thrust as well, right? And there are two wheels, so the distance between the two wheels is called wheelbase. Okay, and obviously and to column distance is your span of the gantry girder. Now to discuss the vertical forces impact load uh, of vertical and horizontal forces, certain stipulation has been given, certain codal guidance has been provided. So this is basically summary of all those things. So vertical forces transferred to the railroad for electric overhead cranes. It is taken as 25% of the maximum static wheel load. For hand operated or manually operated cranes, it is taken as 10% of the maximum static wheel load. Horizontal forces transverse to the rail for electric overhead cranes, it is taken as 10% of the weight of the crab and the weight lifted on the crane. And for hand operated crane, it is taken as 5% of the weight of the crab. Horizontal forces along the rails, that is along the longitudinal direction, it is 5% of the static wheel load. Okay, so we are going to the problem of gantry girder now. This whole thing, the loading, the values of the loading will be clear when we simply discuss discuss this loading thing in a brief manner there. Okay. Also, there is one more thing. There is a codal guidance on the deflection limit. It is provided for different limits for electrically operated or manually operated cranes. Okay. So here is the problem. You have a gantry girder to be used in a industrial building carrying a manually operated overhead traveling crane for the following data. Crane capacity is given as 200 kilonewton. Self weight of the crane girder excluding the trolley, that is the crab, is 200 kilonewton. Self weight of the trolley electric motor hook, it is given as 40 kilonewton. Approximate minimum approach of the crane hook to the gantry girder is 1.2 meter. What is this value? I'll come to that later. Wheelbase is given as 3.5 meter. Center to center distance between gantry rail is 16 meter. Center to the distance between gantry rail means it is the span of the crane girder. All right. Center to center distance between columns, that is the span of gantry girder. So previously 16 meter is the span of the gantry girder, 8 meter is the 16 meter is the span of the crane girder. Crane girder, by crane girder I mean this is your crane girder. This distance is your 16 meter. All right, and the span of the gantry girder, that is the column to column distance, is 8 meter. Then self weight of rail section is 300 Newton per meter. The rail weight of the rail section that will be carrying the wheel. Diameter of the crane wheel is given as 150 millimeter. Okay. Steel is of grade Fe410. Design also the field welded connection if required. The support bracket connection and need not be designed. Okay. So many data is given here. So just simply understanding, making a summary of it. You have a manually operated overhead traveling crane. It's not an electric one. So whatever data that we'll be using, that we discussed previously, will be applicable to manually operated overhead traveling crane. Okay, the crane can take 200 kilonewton load, the hook can take 200 kilonewton load, the crane girder has a weight of 200 kilonewton, and the trolley hook, all of those things has a 40 kilonewton. Okay, and all these data are given. We'll discuss as and when required on the problem. So before we start, I just want to convey to you that today we are only going to find out the bending moment, shear force, how to calculate that, up to loading conditions, up to finding out the bending moment, shear force. We are going to do this problem only. Rest of the problem, I would recommend you, I would advise you to do that on your own, following the problems of the previous modules like beam, plate girder. It will be quite easy when you understand and know the bending moment and shear force. Simply the steps are very simple, but up to the loading condition it is very new, and I believe you need guidance to do that. Okay, so in this video we are going to do only up to the point of loading, determination of bending moment and shear force. Okay, starting with the problem now. So firstly, you simply write down the constants that you already know. In this case, we are using Fe410, so Fe equals to Fe410 and Fy will be 250 MPa. Okay. Uh, for hand operated overhead cranes, we simply discuss the lateral load is taken as 5%, the longitudinal load is taken as the 5% of the weight of the crab and weight lifted. Maximum permissible deflection is taken as L by 500. So these values or these guidance is taken from codes, IS codes. Okay. So next we have partial factors, safety factors and load factors. Now coming to the calculation of design forces. So first we need to analyze, before going into the gantry girder directly, first we need to analyze the crane girder. Again, what is crane girder? Crane girder is this particular portion on which or rather I should say which helps the crab to carry the load. Okay, and this load that the load that is carried by the crane girder is later transmitted through wheels to the gantry girder on both sides. Okay, so to determine the loads on the gantry girder, we need to analyze the crane girder first. So our span of the crane girder is given as 16 meter, that is center to center system with the gantry rails. So 16 meter is the span of our crane girder, and in this case there is one data that is given, that I am yet to discuss: approximate minimum approach of the crane hook to the gantry girder. So if you simply recollect the diagrams or maybe go through Google, uh, you will learn that the hook of the crane girder, okay, or the trolley is a quite huge unit. It simply cannot go to extreme left or extreme right, that is on top of the gantry girder. Like at A point you have one gantry girder here, at B point you have one gantry girder here, and at whichever location within this 16 meter the what can I say, the trolley or the crab is located, at which point of at whichever point, it cannot be directly on top of the gantry girder, because there needs to be certain spacing, or there needs to be certain gap, or as per the term given, approximate minimum approach. That means beyond certain point the trolley or the crab is not allowed to go towards the gantry girder. Okay, and that particular distance is given as 1.2 meter, or it is said that beyond 1.2 meter it cannot go. So we can simply assume that there will be a minimum gap of 1.2 meter in extreme cases where the crane had to move extreme left or extreme right. All right. So there you go, explanation of approximate minimum approach. So here what we are going to do, we are simply going to understand the extreme condition that may occur, which will lead to highest possible loads in the gantry girders, right? Uh, Now if you simply imagine the maximum possible load that will come to the gantry girder in condition when reaction at A or B becomes maximum. All right. So I'll just repeat once more. Maximum loading on gantry girder through the wheels will come only when reaction at A or B at the crane girder becomes maximum, because ultimately this reaction acts as a support to the crane girder, and the support is nothing but the gantry girder itself, right? So this reaction, whichever reaction at A or reaction at B, whichever comes out to be maximum in a extreme condition, that will be the condition that is most likely to cause huge or the maximum load in gantry girders. So simply, like if you remember your structural analysis from third semester, you can simply say that reaction at A or reaction at B will be maximum if the point loads are moved near to the support, right? On exactly top of the support, the reaction is maximum. But in this case, the crane or the hook, there is a certain minimum approach distance, so it can go up to that point, and obviously that point, that particular point will be the will be the critical condition in this case. So simply we have to calculate the maximum concentrated load, and the maximum concentrated load, if you understand, it is caused by the crane capacity, which is to be carried by the hook and the weight of the trolley, or the weight of the, like that unit which controls the whole thing. So in this case you have a crane capacity of 200 and you have a weight of trolley is 40. So in total 240 kilonewton is there, and then you have a maximum factored load on crane, multiply it with 1.5, 36 becomes 360 kilonewton. The other weight, that is the weight of the crane girder, which is given as 200 kilonewton, it will be acting in a distributed manner throughout the span, right? It is not a concentrated load. So the 200 kilonewton that is given weight of the crane girder will be distributed, and the span is 16 meter. It is distributed throughout the span 12.5 kilonewton meter. Again, the factored uniform load is 1.5 multiplied with that. So you have this diagram here, the critical diagram, which will cause a maximum load on the gantry girder, where the uniform load is given as 18.75, and the concentrated load due to the crane capacity and the weight of the trolley is 360 kilonewton, and it will be at a extreme end, left or right, at the just minimum approach distance from the gantry girder. So basically we simply have to determine the reactions here. Simply this calculation just that does that only. Reaction comes out to be Ra equals to 483, Rb equals to 177. So taking 483 at one end, this 483 will be transmitted through two wheels, right? Two wheels are there on each side. So this 483 will be taken transmitted by two wheels. So maximum wheel load on each wheel of crane is 483 divided by 2, that is 241.5 kilonewton. So this 241.5 kilonewton will act on the gantry girder as a concentrated load because it is being passed through a wheel. And what is the distance between these two wheels? Wheelbase is given as 3.5 kilonewton. So if you simply imagine there is two concentrated there are two concentrated loads of magnitude 241.5 kilonewton acting at a spacing of 3.5 meter. Now after analyzing the crane girder, now it is time we move to analyzing the gantry girder. Okay, so as I mentioned, there are two loads which is being passed through two concentrated loads which is being passed through the wheels having magnitude 241.5 kilonewton at a spacing of 3.5 meter. Okay, and additionally, apart from this, you also have a railroad that is acting on the gantry girder, which will be in a UDL manner, uniformly distributed load, and then also you have the self weight of the gantry girder as well. Okay, so let's first discuss how to find out a condition which will lead to maximum bending moment. So if you remember your studies of ILD diagrams, in that topic we had a similar situation when we had to analyze a structure, a determinate structure or indeterminate structure under a wheel of loads. Maybe 2, 3 or 4 wheels of loads are there, and you have to identify the position at which we can place the loads so that the section there is a situation of maximum bending moment coming out. All right, so similar knowledge will be applied here. uh, there was a theorem that to find out uh, maximum bending moment under any series of loads, in this case, to apply that, we simply have to provide or should I say we simply have to place the loads in such a manner that the resultant of these two loads, okay, what will be the resultant of these two loads? Obviously in terms of magnitude it will be 483, but what will be the location of acting that 483? Obviously through this center. So at which point the resultant of these forces are acting, all right, this is the point where the resultant of these forces are acting, right? You have to place this resultant and the any other load, say this one, these two loads, resultant load and the one single load, is to be placed in such a manner that these two things are equidistant from the mid span. I am repeating, resultant of these two loads and one single load should be equidistant from the mid point. That means from this this point to the center of the span, the length will be 0.875. Again, from the resultant of these two loads, from this point, the distance to the midpoint will be 0.875. If we can place the load in this manner under the resultant of the uh, beam, there will be maximum bending moment occurring. Okay, so this way the loads are placed here, and I think this all is discussed here. So simply assuming the self weight of the gantry girder as 2 kilonewton per meter, the dead load comes out to be this one. 300 is the dead weight of the railroad, and factor dead load you have, and then simply they have calculated the position of one wheel load from the midpoint of the span, and then the bending moment due to live load only. Live load means the load due to the wheels. Okay, so that way they are finding the bending moment. First taking out moment about D, they are calculating RC, and taking moment about C, they are calculating RD. Okay, so this way they have calculated the reactions. Moving on, they have found the maximum bending moment due to live load and bending moment due to the impact. uh, Due to impact, it has been taken as 10%. Total bending moment due to live load and impact load found out to be this value. Now bending moment due to dead load is taken as WL square by 8. Maximum bending moment is taken as, if you simply add them up, you have the results. Okay, now coming to maximum shear force. Again, maximum shear force will occur when the loads are placed near the supports. So in this case, you have a series of two loads, two wheels. So one load you can put directly on the support, and the other one will be at a distance 3.5. So simply by taking this orientation, you can find out RC, and that is the maximum shear force it will be experiencing. Now coming to the lateral forces, you have to simply calculate the lateral forces following the guideline. Lateral force transverse to the rails, 5%, it is taken as 5% of the weight of the crab, and the weight lifted, so which is 40 plus weight lifted is 200, comes out to be 12 kilonewton. Factored lateral force is coming out to be then 1.5 into 12, 18 kilonewton. Lateral force on each wheels, there are two wheels, so 9 kilonewton. Now they have simply used the method of proportionality, not undergoing the whole calculation once again. Simply used the method of proportionality, and then find out all those things: maximum horizontal reaction due to lateral force, horizontal reaction, then finding due to lateral force at D, maximum bending moment due to lateral load, again by method of proportion they have calculated. So these all data has been calculated using the method of proportion. Okay, so up to this point we have calculated the maximum bending moment, shear force, and lateral forces. Okay, you see from the next step there is a design starting. So I'll recommend you to start your design based on this data. Try to do it by yourself. If not, obviously I'll be helping you with a video next week through the design of gantry girder overall. uh, so that's it for today. See you in the next week.